Test. Okay, cool, I'll start. Good afternoon, everyone. I'm Francis, and with my co-speaker, Thirwell, we're here to talk to you about HBase multi-tenancy using region server groups and favorite nodes. This is how we do it at Yahoo. Okay, let's start. So let's start with a quick overview of HBase at Yahoo. So since we released HBase as a hosted service at Yahoo a few years ago as part of the Hadoop service, Hadoop as a service technology stack, HBase has been widely adopted across a lot of products at Yahoo, be it from like Yahoo Gemini for ad targeting or things like that, to like Yahoo Mail, it helps power features in Yahoo Mail, to like powering features such as content personalization in the Yahoo front page. So as you can imagine, the use cases vary from data warehousing to near real-time processing, OLAP to OLTP. And as you can imagine, we use a bunch of different frameworks or applications to actually meet these use cases. And so these are generally like the usual suspects that produce workloads on HBase. So you have for batch, Pig, and Hive, and Spark for batch processing, and for Storm for near real-time processing, and then you have Uzi for scheduling. So as you can imagine, these different frameworks. Oh, and we also have users using other custom applications and other frameworks, but these are the most common ones, and these are the ones we actually support as the Hadoop team. And so as you can imagine, these different frameworks, different applications produce different pressure on the region server resources. And just to give you an idea of this pressure, this is basically a throughput graph of one of our multi-tenant clusters. So as you can see, it's pretty chaotic. And as you can imagine, these applications have bottleneck on different dimensions of region server resources, be it CPU or memory, or more specifically like region server resources, such as the block cache, memstore, or even the handlers. So to put that more into perspective, here's some more information about this one multi-tenant cluster. So in this cluster, we have around 45 tenants, around 940 region servers, around 300,000 regions, and the top line of that graph is around 115 requests per second in terms of throughput. So yeah, so as you imagine that we have these many tenants running all these various things. How are we able to like make sure that no one is stepping on each other? Everyone gets the resources they need, meet their SLAs, and everyone can move forward? Well, our answer to that was region server groups. So what region server groups are is basically you can create a group. It's a logical group, and then you can assign member tables and member region servers to that group. And what that basically means is that all the tables within that group are pinned to region servers, only to region servers that are members of that group. So basically what you have is this coarse level of isolation that basically no other regions from other tenants are actually using region servers that have been assigned to you. So what this gives you a nice coarse isolation, so you basically don't have any resource contention on CPU, memory, or anything specifically to the region server, such as block cache or memstore. What this also gives you is that you're able to configure each region server differently for to streamline it better for a specific tenant. So you can potentially have bigger block cache in some groups, and then or potentially have more handlers, or even tune the GC, because generally that would be a problem for different workloads. Not only that, but there's also namespace integrations with region server groups. So what that means is that if you can tie a namespace to a region server group, so that when you create a table, that table actually gets assigned automatically to that region server group. So basically, region server group is a divide and conquer strategy. So what you do is you have this giant cluster, and then you basically cut up a set of region servers, and then assign them to groups. And so here, on the right side, that's basically the same source of information for the throughput graph as the previous graph, except that I'm only selecting a certain set of region servers. And those are region servers from the same group. As you can see, it looks less chaotic. It's more periodic. And so what this means is that we're able to tune the region servers in that group for that particular workload. Thereby, we're more able to efficiently use those region servers. Not only that, it's also easier to sort of identify any anomalies. Another good thing is not only are you isolating resources, but you're also isolating failures. So what happens is sometimes, especially when users are, start their new product or application, they tend to, whatever it is tends to be buggy, and they tend to bring down servers. And so in this way, if some user starts some new application and cause problems, they only cause problems for their region servers and doesn't affect the other users. So more numbers in terms of the region server groups. So in this cluster, we have around 45 namespaces, 45 region server groups. We essentially have a namespace per region server group. Each region server group spans from just 4 region servers up to hundreds of region servers. And region server groups can have, at least these ones have at most 2,000 regions per server. So as you can see, thanks to region server groups, we're able to support a diverse range of different workloads, different kinds of tenants. And not only that, we're also able to support tenants we wouldn't have been able to. Like, for example, if you have a tenant that just asks for 4 region servers, it would not make sense to build out a cluster just for them. It would be a lot of operational overhead. So thanks to region server groups, we're actually able to support these tenants as well. So how do you provision a region server group? So it's actually fairly easy, and it's non-intrusive. So this is how we would do it at Yahoo. So essentially, you basically add a group using the add group command, and then you add servers to that group. And the servers, basically, these are servers, you make sure that they're not being used from other groups. So by default, if servers are not members of any group, they are members of the default group. So you basically just look at the default group, figure out which servers you want to use, add them to this group. And then after that, you tie a namespace to a group. So you create a namespace, you tie it to that group, and finally, you create your table, and it becomes part of that group. And there you have it. You provision something for your user. So let me walk through the block diagram. So this is operationally, this will also be useful so that you know how it works and how you potentially debug it. So the way it works at its heart is basically the RS group-based load balancer. So load balancer is this thing in HBase which runs in the master. And what it does is whenever a region needs to be assigned, it asks the load balancer. It does this by sending it a set of region servers and regions for it to assign. And the load balancer will spit out an assignment of region servers to a list of regions that it's supposed to go to. So what we've done is we basically created this RS group-based load balancer, which doesn't actually do any balancing. What it does is it takes that input, groups those set of servers and regions by region server group, and feeds them group by group into the load balancer. Thereby, we guarantee that all the regions only go to region servers that are part of the same group. And below that, we have the RS group info manager, which takes care of persistence. And basically, we persist the region server group information in 2 places. One is in an HBase table, and one in Zookeeper. We put it in Zookeeper as for cases where you would need to basically bring the cluster back up. So during this time, the HBase table is unavailable. So we read the information from Zookeeper. And then finally, we have a coprocessor which serves all these the APIs that you just seen previously. So to add region servers to a group, move servers, and so on and so forth. So this is the basic region server group feature, and this is what's available in HBase 2.0 when it releases. Let me talk about the other features that we have internally at Yahoo, and we are working to push it in open source and possibly as part of HBase 2.0. So one is group metric tagging. So basically what this means is that each region server, when it publishes metrics reports, it will tag it with region server group information so that when all you have to do is click on that particular tag and see region server metrics for that particular group. This is better than getting the list of servers that are part of that group and looking it up, because this way you get historical information. So you get information about region servers that were part of that group but are no longer part of that group, but they were at a certain point in time. Next is we added dead region server thresholds. So what this means is that whenever you provision a group for a tenant, we usually provision a little slack in the event of servers potentially dying. And so when there are too many servers that die, then that means that there is no longer enough capacity in that region server group to support that workload. And so what they decide to do is we no longer assign regions to that particular group until the number of servers that are alive are enough to actually support that workload. This way, it prevents any more chaos into that group. It makes it also potentially easier for us to recover that group once we brought up the other servers. Next is dead region server processing. So the way dead region servers are processed, whenever a region server dies, there's a server crash procedure worker that takes work out of a queue and then processes the region server, the dead region server. What that means is it'll split the write-ahead logs and it will assign the regions. And so in the case where in a specific group there's cascading failure and there's a lot of servers that died, what might happen is servers from other groups that have a few servers that died get starved because they're all in a single queue. So what we've done is we've added multiple queues and added fair scheduling so that no single group will actually starve the other groups. Finally, we've also added made replication group aware. So what this is for those that don't know how region server replication works, is basically there's a thread in the region server called the replication source. And what it does is it picks a sync server at the slave cluster, and then that sync server gets shipped the information that needs to be replicated, and then the information gets replicated locally. So the problem there is that that sync server can be any server in the slave cluster. It doesn't have to be from the same tenant. So what we've done is we've made the region server aware of what group it is, and then it picks a sync server that has the same group name as the current region server. So we never use any other tenant's resources to do replication. Also, to add to that, we've also made it so that whenever a region server dies, the write-ahead logs that need to be replicated, those are recovered only by region servers that are part of the same group. So this is how we made replication group aware. So here's a laundry list of things that we sort of do with region server groups at Yahoo. So as I mentioned, we have per group configurations at Yahoo. So GC, memstore, you name it. So basically, whatever you can see in HBase site XML and HBase SH, we configure. And it's been very useful for us. Another is, whenever for our production clusters, what we do is we always create a system group. What that is it's basically a group where we put all these system tables in, meta, ACLs, those tables. What this gives us is that it makes these tables very highly available, because normally what brings region servers down and meta down is user regions that are co-located to the same server. So it either starves that server or it takes it down. So this way, since the workload is basically just meta access, it generally tends to be very available, and the region servers rarely go down. And a lot of our operations, a lot of them work at the per group level. So we have rolling upgrade per group. We have rolling restarts per group. So we do that because we tend to like to push configurations on a particular group when we're still iterating and tuning it until it fits a particular workload. The other thing we do is we have different balance strategies per group. So we balance per group, but also we tend to have different ways of balancing it, either using the stochastic load balancer or the simple load balancer, or a balancer based on locality. Though we're trying to move on to like just a single balancer, which Thirwell will talk more about in his section. And then we also have alerting or monitoring per group. But what this means is that we not only care about the health of our cluster, but we care about the region servers that are tenants, that will affect our tenants. So basically, we have information such as if we have too many servers that die in a particular group. And finally, we make use of the namespace integration a lot. So basically, this is very useful, especially in our sandbox cluster, where we allow our users to create their own tables. And so this makes sure that these tables actually end up in the resources or the region servers that they were actually allocated. We also make use of table and region quotas a lot, because table and region quotas are things that make use of shared resource, such as the HBase meta, and the table descriptors, which are all cached in the master. So that's the end of my presentation, and let me turn it over to Thirwell, who will talk about favorite nodes. Thank you.
So hello, everyone. So I'm Thirwell, and I'll be talking about what favorite nodes is, why is it important, how does it work in general, what enhancements we have done, the tooling around it, and some metrics from our production clusters. So at a high level, you can actually provide block placement hints when you actually create a file in HDFS. It's basically an array of data nodes. That's what we call favored nodes from HDFS perspective. In HBase, we can actually allow region level block placement hints. It's basically at a region level we assign a set of favored nodes or data nodes, and all the files that are created as part of the region will actually use those favored nodes. So that's at a high level, providing block placement hints at a region level. So why do we need it? Data locality. We want or we strive to reach at least 100% data locality. When you have 100% data locality, it basically helps in a better performance for the whole system. So you don't have to go to a remote data node to fetch a block in case you actually miss the block cache. Now, if you stop going to remote data nodes to fetch blocks, then you actually make better use of the network. You can see all of these in the graphs that will follow. And in a multi-tenant setup, like you have like 45 tenants in a single cluster and a single HDFS instance, each group will actually have, or each tenant will actually have different characteristics. So we can also provide Datanode isolation at a group level. So those are the motivations. Now, there was a prior work that was also in the community before this, but that was it was done by the community, some of it was also done by Facebook. But that was extremely hard for us to use, pretty much impossible. And as far as we know, no one in the community uses it either. So how do we enable favored nodes? So we have a couple of balancers, and you have to change your master to use the favored node balancer and just restart master, and you have favored nodes. That's all. That's all you have to do. And if you have a very large cluster like ours, you can actually create the favored nodes for all the regions upfront before starting the master. That basically means your master will start up fast if you have like 300K regions and stuff like that. And there are a couple of configs from HDFS perspective. So since we actually run a region server and a data node on the same machine, and we don't run yarn or node manager, we actually turn off the HDFS balancer. So how does it work in general? So once you enable favored node balancer as part of the master, whenever a new region is created, it actually creates a list of favored nodes for that region. And it has an in-memory cache, a favored node cache, which basically has this mapping. This information is also persisted in meta. So when the master comes back again, it looks at meta, constructs this cache, and then proceeds forward. So a list of favored nodes is basically a list of region servers or data node here, that's all. And when assignment manager tries to open a region, it actually sends an open region request to the region server. Now, as part of the request, it basically sends, hey, this is the region I want you to open, and these are the list of favored nodes for it. Now, the region server basically gets that mapping, and it has an in-memory cache where it maps the region to a list of favored nodes. Again, it's the same thing. So when there is a flush or a compaction happening for that specific region, it reads this cache, and it has an array of data nodes. And whatever file it creates on HDFS, it uses that array, and then it provides hint to HDFS. Now that's how a favored node is created, persisted, passed to the region server, and used essentially when you actually try to create a file. So the list of enhancements that we have done is predominantly in open source. It's in open source Jira 15531. It also has a design document that actually documents everything, all the tools that we are going to talk about here. So at a broad level, we have two balancers that we have introduced. So one of the balancer is already checked in and was part of the HBase 2.0 alpha release. The other set of tools are predominantly admin and operational tools. So we'll walk about all of them. We have a couple of diagrams. So favored stochastic balancer is at a cluster level when you don't have region server groups. It basically extends, or it's similar to the stochastic balancer that is already in HBase. And it is favored node aware. What that means is when a region is assigned, it is assigned only to one of its favored nodes. A region can have 3 favored nodes. So when the balancer is called to assign a region, it assigns it to one of those 3 nodes. It has a couple of pickers or candidate generators, and we have some costs that are associated with it. So this creates a favored nodes only for user tables. So we don't do it for meta or anything like that, because the system tables are in memory, and 99.99% of the cluster is just user tables. So we do it for user tables to start with. The other balancer that we have is the favored RS group load balancer. So that is basically group aware. And since it uses the favored stochastic balancer, it is also favored node aware. So it is all assigned within the same group and within the favored nodes for that region. So what happens when a region splits? A region could actually be 10 GB or sometimes even 100 GB. So when it splits, we don't want to lose locality. So we inherit two regions, two favored nodes from the parent, and we generate one randomly. So this gives us a good balance. You have very good locality even after the region splits, and you also have a good distribution. So we did a bunch of tests, and we started with one table. We had like 10 servers, and we kept on splitting. We went all the way up to 1,000, and we finally had a pretty good distribution. So the default logic works pretty well. And what we do for merge, we just inherit it from one of the parents, and you just have locality, all the locality. So the region and favored nodes. So this is extremely important. Why? Because the balancer uses it, and you want overall uniform load across the cluster. When a region server crashes, you don't want one or more servers getting overloaded. So what we call as distribution, it's basically the replica count distribution. How the favored nodes are assigned to the regions. So we'll call it as FN replica, just for namesake. Now, please do not confuse this with region replicas that is already in HBase. Now, those are like different topics. So this is a sample distribution. Just for namesake, we'll just call primary, secondary, and tertiary as the three favored nodes. But all we care about is the total distribution. As long as the total distribution or the total count per favored node is more or less equal, the cluster will be well balanced. Now, that is a distribution. Now, how do you change distribution? So when a region is created, favored nodes are created. Now, how do you change it? So you want tools that will basically help you spread the favored nodes across the cluster or the group. So the three tools we have are redistribute, which basically balances out. And as you can guess, it is something that is less invasive. And we have a complete redistribute, which is basically the nuclear version of redistribute. And when you want to remove a node, you can basically use the remove favored node. We'll talk about redistribute and remove favored nodes in the next slides. Now that's a command that we have. And the open source version may or may not change, but it's going to have the same syntax. So redistribute is used, it's also used when you actually want to add new servers. So in this case, let's just add a new server, RS5. You can follow the same commands that Francis talked about. So once you add a new node, that node does not host any regions now, and it's not part of any favored nodes. So once you do a redistribute, one of the regions, so the redistribute basically understands that RS5 is underloaded, and RS4, it has two regions, is overloaded. So it basically takes from overloaded servers and creates favored nodes from underloaded servers. So one of the regions will actually have RS5 as a favored node. Now redistribute does not change any current assignment. So it just runs, changes the favored nodes, and walks away. Once you run balance, the region will actually move to RS5. And the data blocks don't move yet. And once you run compaction, the data blocks will actually move to DN5. So you can actually run redistribute very frequently, and it won't disturb your cluster. It'll just change the favored nodes in the backend, and it won't disturb your cluster. Now, the constraint that we have is, if a region has at least two favored nodes with more than 80% locality, then we consider that for moving around. So if you have regions with less than that, then we don't touch them. So the same thing applies for removing a favored node. So if you want to decommission, let's say RS5, and when you run a remove favored node, it removes it from the list of regions that it has, and then once you do a balance, it moves out. And then you can run HDFS decommission, which will basically move out the blocks. Or if a compaction happens, they'll eventually move away. And then you can take that node out of rotation for maintenance or for whatever you want. Again, the syntax is that the host name and whatever the region server port you have. Now let's look at why we want to do this. Data locality, performance, network utilization, and the isolation. So we have been running favored nodes in our production clusters for the last 18 months. And even on multi-tenant clusters, we have been running it for more than a year. So let's look at some graphs. So we ran Chaos Monkey test, which basically on our dev cluster. Now, without favored nodes, if you can see that the locality drops as soon as the chaos begins. So the region servers are going up and down, and then the regions are getting moved, and it's not assigned and you actually lose locality. Now it actually has 100% locality to start with. Now this is the worst case scenario. Now what happens if you have favored nodes? The locality stays at 100%. It never goes around. The balancer only assigns to a favored node, and hence you always have 100% locality. The only dips you see here is due to the metric system. This is one of our largest sandbox clusters. Let's run it at scale. So this has 2,500 regions, and as you can see, it has only 60 to 80% locality. We didn't compact the whole table, so intentionally. Now, I do a rolling restart. As part of rolling restart, I unload all the regions on a region server. I restart the region server, and then I move to the next server. I do it for the whole group. Now, when this happens, as you can see, the locality doesn't change. It pretty much stays from 60 to 80%. Now I'm moving thousands of regions around. A single region server actually starts from, say, 2,400 regions and goes all the way up to 4,000 regions. You don't lose locality. Now, after the rolling restart is done and the balancer is running, say it takes at least 1 day to actually catch up to a uniform state, you can see that there is pretty much no change in locality. It stays pretty much flat. You have thousands of regions moving around. So chaos monkey test or rolling restart at scale, balancer at scale, you have data locality. Now let's look at Datanode Isolation. So we looked at the disk used percentage on at least 2 racks on our production cluster. Now this is over a period of 3 months. Now both of them have the same set of tenants. Now tenant 1 or group or customer 1 is storage heavy. They use a lot of disk space. Now tenant 2 and 3, they are not. They're very, very lightweight. Now before we had favored nodes, the disk used percentage is more or less uniform or actually distributed. It doesn't really correspond to anything because the block locations are chosen based on whatever HDFS decides. Now after we have favored nodes, the disk used percentage matches what the tenant's characteristics are. So it's 50 to 60% usage for tenant 1 and about 10 to 20% for the others. So during this whole period, for both the groups, the table size or the region size were pretty much constant. Now we have isolation at the data node level, even if it is on the same rack. Now once you have 100% locality, your remote data node reads should actually go down, right? Now this is a 2-week graph on one of our multi-tenant cluster which has like more than 200, 300 nodes. Now, before we had favored nodes, there is a lot of remote data node reads happening. And after we have favored nodes, it's pretty much gone down to 0. The only spikes you see are more or less random, and they're more or less on the same set of servers. I'm not sure if you can see it on the presentation, but it's more or less on the same set of servers. Now, that is because we actually have health check scripts running from the gateway machines and just trying to check whether the cluster is safe or not, or healthy or not. So they are not HBase traffic. They are just health checks traffic. Now, how does the read traffic look like during the same period? Again, at a cluster level. Before we had favored nodes, it oscillates somewhere between like 3 to 4 million, the read request rate. And after we have favored nodes, it crosses somewhere between like 6 million. Again, I'm not sure if the metrics are looking good there. So we have more reads, but the remote data node reads has pretty much gone down to 0. And we also looked at the write request metric during the same time. It actually went 3x higher. This is over a period of 1 year. Now, if the remote data node reads are actually going down so significantly, how should the network utilization look like? Now, this is the max input and output bytes per second. And this is aggregated on all of the top of the rack switches at a cluster level. And this data is for 1.5 years. Now, since it is a max input and output traffic at the TOR level, it includes both HDFS and user traffic. So user traffic, gets, scans, puts, whatever you want is included in it. And the write pipeline, flushes, everything is included in it. So it's all the traffic, cross-rack. So the y-axis is actually drawn to scale. Before we had favored nodes, as you can see, for about 7 months, we actually enabled it sometime last July. It oscillates, the max input and output bytes oscillate somewhere between 20 to 40 units. And it oscillates like so much. After we enable favored nodes and once the compaction are actually done, you can see that it pretty much stays at 20 units. And we also saw on the same cluster, a couple of slides before, the user traffic actually went up. Now, even with increase in traffic, you can see that the max network utilization went down significantly. The only spikes you see are actually scheduled maintenance when we, just for a set of days, we actually had to do some work and we disabled the favored nodes and just went with non-favored nodes. So at a cluster level, at a network utilization level, we actually see so much of benefit. So from monitoring perspective, so we have, if you have HBase, you actually run HBCK to actually check the cluster state of the system, health of the system. So we added a bunch of checks to actually check how the favored node distribution looks like and whether there are any corruption there and stuff like that. And we also have tools that actually helps us to know how many dead nodes are favored nodes, and we have JMX endpoints, which basically tells us, hey, you have one favored node dead, and that is impacting 1,000 regions. You have two favored nodes dead, that is impacting like 300 regions. So you can look at that, and we generate alerts, and we can quickly act on them. And in the worst case, when all three favored nodes actually crash at the same time, the region will not be assigned because none of the favored nodes are online. And if you look at the master UI, you will get a clear message that all the favored nodes are down, I can't assign you. So in summary, the production experience that we have is overall, the cluster locality has actually gone much higher and continues to grow once we enable favored nodes. As our best practice, we run redistribute every day. And if there is nothing, if there are no underloaded servers, then the redistribute is basically a no-op. In the future, we'll convert that into more or less a thread that runs in the master. There are some scenarios when the favored node hints will not be taken. For example, if the data node is actually getting decommissioned and it takes a long time to decommission, the name node will basically not choose that hint. And another scenario is if there is a HDFS rolling upgrade happening, or if you're just rebooting the machines and stuff like that, the hints won't be taken. Other than that, for the most part, the hints were actually taken based on 1.5 years of running favored nodes. Otherwise, we had some bugs here and there that actually were actually fixed, and for the most part, the cluster has been stable for a really, really long time. That concludes my presentation, and we have about 8 minutes for questions. Thank you.
Are there some tests that were run with RegionServerGrou and favored nodes in combination?
So the question was, are there clusters run with region server groups and favored nodes in combination? Yes, that is the intent actually. So we have 2 production clusters running with these 2 running in combination.
3 actually.
3? Oh, 3. 3, right, 3.
Was there some benchmark done when you had it running in combination versus having like the favored node run in isolation?
Right, so the graphs we've shown you, those were all those clusters actually.
Okay.
Yeah. Sorry, yeah, go ahead.
The region server groups, are they separate processes? How do you achieve the isolation?
The question was, are the region server groups separate processes? So the isolation is basically a region server group is exclusive to a particular group. So basically, it's exclusive to a set of tables that are members of that group. So it would never be used in another group, which is for another tenant.
It's all within the same JVM.
So the region server is with its own JVM, which is tied to one host. So it should never share. No 2 region servers run in the same JVM. Right?
Basically, it's a node level. It's not like at a JVM level. That's what you're saying.
Yes, yes, it's at the host level. Yes, right, right. Okay. Yes, go ahead. Sorry, it's the guy behind you. Sorry. Yes.
What happens when you fill a group?
Sorry, the question is what happens?
If there is no space on some group.
Oh, you mean disk space?
Yeah.
Okay.
Memory space.
Okay. So the question is, what happens if you run out of disk space in a group? So I mean, basically, the name node will just reject your favorite nodes, and it will get stored at some other place.
This is from the region server, so region group.
Yes. By space, what do we mean here? Like memory or? Okay. So, so basically what will happen is this is how HBase works, right? Whenever machines go down, they just get reassigned. So in this case, I guess the question was what happens if region servers die and there's not enough capacity? So, so basically if region servers die in a group, they just end up getting assigned to whatever region servers are online, right? And that might potentially overload these servers. And so that's why we've added that feature, the dead region server thresholds, so that once your region server group has gone below capacity, we stop assigning the regions. It's to prevent further cascading failures on that group, because obviously that group will no longer survive, right? So I think it's two things, right? One is it's a question of capacity, right? So when you provision a group, you have to provision some amount of slack because you know some servers will go down. Right? Beyond that, then it's a matter of basically you coming in and fixing it and making sure that you can recover from that failure. So if you need high availability, then you should have probably another cluster, right? If you really care that your application is always up. Sorry, go ahead.
The replicas are on the same rack, right?
Are the replicas in the same rack? So, sorry, do you want to answer that?
Locality,
Yeah, so one of the recommendations we have is when you create a group, you have, I mean, even if it's the smallest group, we ask you to create at least 4 nodes in a group. That's the smallest unit. And it's better if you actually create it across 2 racks. So even if a rack goes down, there is a problem with top of the rack switch or something like that, or if you have to reload it, software updates, you have a backup. And that also, obeys the HDFS.
the favor node is that it's on the same rack. Right?
No, favor nodes is basically 3 data nodes, right? So you're basically telling HDFS for all the files, for all the H files flushed, created as part of this region, use the same set of data nodes, that's all. So if the group itself is spread across 2 racks, the favor nodes will actually be chosen accordingly. So it will always be.
Locality is not guaranteed, right? You're saying the network is safe, that the traffic is safe because of this favored node.
Okay.
Is that correct understanding? I'm not questioning, I'm trying to understand.
So if you have say 4 nodes in a group and 2 nodes are in one rack and 2 nodes are in another rack. So when we create a favor node is basically 3 nodes. So we choose one primary, secondary, and tertiary. So this is where the blocks are. So if this rack goes down, it will be assigned to the regions over here, the host here, which is actually a favor node of it. So that way you still get 100% locality. And for larger groups, we distribute it across 5 racks, 10 racks, and stuff.
So one more question, I guess. The guy behind you asked first. Yeah.
Does the RegionServerGrou feature impact the authorization on the HBase? Or the authorization didn't have to change in the instance of the HBase?
Okay. So the question was how does RegionServerGrou impact authorization? So it remains the same. So the way it works is if whoever has access to the table can access the table. Doesn't matter which group it's on. Right, so, okay, I guess that concludes our presentation. You guys can come over and ask us more questions if you want. Thank you.
Okay, thank you.